Okay, so let's look at another example on mixing problem. Um, so it reads like a tank contains 200 liters of fluid in which 30 grams of salt is dissolved. 30 grams of salt is dissolved in it. Brine containing 1 grams of salt per liter is then pumped into the tank at a rate of this. The well mixed solution is pumped out at the same rate. Okay, so right now we know that the model should take the form the T is equals to R in minus R out, and we know that our R in is equals to concentration in times inflow. Okay, and then R out is equals to concentration out times outflow. So take note of these things. Now this one, A of 0 should be equals to maybe something. Now let me write this. Now okay, I'm coming. Let's identify these things first. So a tank contains 200 liters of fluid in which 30 grams of salt is dissolved in it. So it means that initially or at t equals to 0, A of 0 is equals to 30 grams. That's the concentration of salt. 30 grams. Okay, so now brine containing 1 gram of salt per liter is then pumped into the tank at a rate of this. Okay, so R in is equals to brine containing 1 gram of salt is pumped into. Okay, that's in. So 1, that's the concentration in times the rate, 4 liters per minute, 4, and this gives me 4. Okay, this is the rate in. So this one you can get it maybe so this is just 4. So now the R out equals to the C out, the concentration out C of T is equals to A over volume plus change in rate times time, like this. Okay, now the C out, the amount we don't know what is coming out, the concentration, the amount of substance coming out over the volume. What is the volume? They said it contains 200 liters of fluid. Okay, so the initial volume 200 plus the change in rate. Change in rate, what comes in minus what goes out. So they said what comes in into the tank is 4 liters. It's 4 liters, this one, and then what goes out is the same rate. Okay, so it means 4 minus 4 times the time, and so this becomes A over 200 because this gives me 0. Okay, so right now we now have the concentration out, which is this figure here. So that's A over 200 times the outflow. Outflow is also 4. Okay, because they said the water goes out at the same rate, and so with this you get 4A over 200, like this. Okay, so right now we don't have to write our differential modeling, so we have the A, the T to be equals to the rate in. Rate in is 4, so we have 4 minus the rate out, which is this, so 4A over 200. Now initially A of 0 is equals to what? A of 0 is equals to Good. Is equals to 30 grams. 30. Okay. So we then have to solve this particular one. So let's see. Yes. So yeah. So find the number of. So the first one is find the number 80 of grams of salt in a tank at time t. Okay. So we are just going to solve this particular IVP. So let's see. So we have the A, the T goes to 4 minus 4A all over 200 like this, which will imply we have the A, the T plus 4 over 200 A equals to 4 like this. Okay. So right now we use the method of integrating factor to solve this. You know that the integrating factor mu of t is equals to e power this integral of this value here 4 over 200 dt, and this becomes, in fact, this for one, that's 1 over 50, so that will just be e power 1 over 50 t like this. Okay, so this is our integrating factor. So right now we can then use this integrating factor to write our solution. So a of t will become the integral of q of t. What is q of t? That is just the 4 that is here. That 4. So this 4 here is our q of t. So we have 4 times the integrating factor, which is e power 1 over 50 t plus c, all this over e power 1 over 50 t like this. Okay. Yeah, b2, let me see, 200 to 50. 4 divided by 200, 1 over 50. Yeah. So here we integrate as usual, and then if we integrate this, that will just be 4 times 50 over 1 e power 1 over 50 t plus c is over e power 1 over 50 t over e power 1 over 50 t. And so here we'll get 200 e power 1 over 50 t, but you know this and this will cancel each other, so I don't even need to bring this again. So just get 200 plus c e power negative 1 over 50 t. That's our a of t, but we have our initial value, initial volume or initial amount, which is 30 grams. So at t equals to 0, a of 0 is equals to 30. So this will imply that we have a of 0 to be equals to 200 plus c e power negative 1 over 50 0 equals to 30 like this. So this will imply that we have c e power 0 equals to 30 minus 200 equals to negative 170. So this implies that c is equals to negative 170. So we then rewrite our function. So a of t is equals to 200 minus 170 e power negative 1 over 50 t. This is our model for the problem. So now we've got the solution. So this is the a part of the solution. They said we should find the amount A of t at any time t. At any time t. Okay. So now let's go for the second part of the question. The second part is, what is the amount of salt in the tank after a long time? Okay. So we want to find the B part. Okay. The amount of salt in the tank after a long time. Okay. So it means that a long time, you don't know that long time. So we will take the limit as t approaches a very long time. Let's say infinity of A of t. Okay. And this will be equals to the limit as t approaches infinity of 200 minus 170 e power negative 1 over 50 t. Okay. But you remember that this is the same as the limit as t approaches infinity of 200 minus 170 over e power 1 over 50 t, like this. Okay. Now, as the t goes infinity, as this t becomes big and big and big, the whole of this will go toward 0. Okay. If this t here becomes big, very big, like billions over billions, this thing will become very big, so the whole of this goes to 0. So therefore, and the limit of a constant is the constant, so we have the limit as t approaches infinity of A of t to equals 200 grams of salt. And this is the B part of the question. Thank you for watching. Kindly subscribe.